Okay, now we're moving on to summary evaluation. So summarization is a very interesting problem in natural language processing, but a sub-area of summarization that is just as interesting is evaluation. So how do we evaluate good summaries? Well, there are many different criteria. Some of them are, is it the right length? We don't want something that's way too short or too long. Is it faithful to the original documents, balanced and all? Does it capture the most salient information? Is it grammatical? Is it non-redundant? Is it well-formed referentially? That means that it has the right connectives and doesn't make any false implicatures. Is it structured properly? Is it coherent? All of those are important evaluation criteria, and there has been work on all of those in the research community. Some of those are not specific to summarization. For example, grammaticality and coherence and so on also apply to text generation in general, also to machine translation, and even to question answering. Whereas length, salience, and some others are specific to text summarization. So let's step a little bit back here and think, what would be an ideal evaluation for summary? What does a summary really achieve? Well, it has to do with the idea of a compression ratio and a retention ratio. So the compression ratio is essentially what percentage of the original document is preserved in the summary. And the retention ratio is what percentage of the information in the document is preserved in the summary. So what we want is to compress as much as possible while retaining as much information as possible. So ideally what we want is the retention ratio to be larger and possibly much larger than the compression ratio. So if we can have a 10% summary which preserves 80–90% of the original content, that would be a really good summarizer. So what are the different evaluation methods used? Well, there are several categories. The first one is extrinsic techniques or task-based techniques. For example, you give one set of users the full documents and you ask them to classify them using different categories. And then you give another set of users summaries of those documents and you give them the same task. If the users who have access to the shorter documents are able to do the classification task just as well as the ones who have access to the full documents, and perhaps take even less time, that means that the summary has done a good job. And the task could be something different. It can be a question answering or routing and so on. There is another category of techniques for evaluation of summaries called intrinsic techniques. In that case, you take the output of the summarizer and you compare it with possibly a golden standard summary or with another summary. So the most simple technique for intrinsic evaluation is based on precision and recall. You're probably going to see this description multiple times in this class. Precision and recall are very important for word sense disambiguation, for parsing, for summarization, for many other tasks. So let me give you a little bit of background here. We have a 2x2 table that has two rows. The first row corresponds to the cases where the system thinks that a certain document is relevant to the query. The second row matches the documents that the system thinks are not relevant to the query. The first column talks about the documents that are relevant, and the second one is the ones that are not relevant. So the example that I just gave you has to do with document retrieval. Now, how does it relate to summarization? Well, in that case, we have a gold summary, for example, 2 sentences picked by human judges, and we have a 2-sentence automatic summary that consists of possibly some other sentences. So in this case, relevant corresponds to the sentences that are in the gold standard summary. Non-relevant means the sentences that are not there. System relevant means that the sentence is produced as part of the output of the summarizer. And system non-relevant corresponds to the sentences that are not produced by the summarizer. So A and D are the numbers that give us good performance. So the more cases we have where A and D are high and B and C are low, the better our system is going to be. Okay, so the metrics that we're going to use here are precision and recall. So precision, or P, is A divided by A plus B. So A plus B is all of the sentences that we produced as part of the summary, and we want to see of those how many were in the gold standard. Recall is A divided by A plus C. So this is out of the sentences that were in the gold standard, how many did we pick? And we can also define F or F1, which is the harmonic mean of precision and recall. And the purpose of using F is so that we have a single metric and we don't try to optimize either P or R at the expense of the other one. So another technique used in summary evaluation is Rouge. Rouge was introduced by Chinyu Lin and Ed Hove in 2003. It's an automatic metric that's very easy to prototype. Even though it has a number of flaws, it has been widely adopted by the summarization community because it's very convenient and easy to prototype. It's based on Papineni's 2002 paper on BLUE, which is another metric based on content used for machine translation. Let me explain the difference between the two. In BLUE, you're trying to get, you will get a high score if your output has a high precision in terms of 1 grams, bigrams, trigrams, and so on, compared to the reference text. In Rouge, you have a high score if your recall of the original content, of the gold standard content, is high. So that R in Rouge actually stands for recall. So Rouge N is a variant of Rouge that is used to measure n-gram overlap between an automatic summary and a set of reference summaries. So the idea is that you don't expect that there will be only one great gold standard summary. You allow for the possibility that different human judges are going to produce different summaries that are going to be different from one another. And then you want your system not to be exactly the same as any particular one of the human reference summaries, but rather that it should be similar to all of them at the same time. So Rouge L uses, instead of n-gram overlap, uses the longest common subsequence of words between the automatic summary and the reference summaries. So Rouge is very useful because it has been shown to correlate with manual evaluations, but at least when it's averaged over many different sentences. So why is this important? Well, because manual evaluations are very expensive, whereas Rouge is automatic and can be computed very easily. The only thing that you need to do is to have gold standard summaries by multiple humans. Rouge has some problem that it can be easily gamed, but this is something that is not that much of a concern. Another metric related to Rouge and precision and recall is relative utility. So relative utility takes again into account the fact that there may be multiple correct summaries or multiple gold summaries for the same set of documents. So let me give an example here. Suppose that we have one reference summary of 2 sentences picked out of 10. That's the ideal column in this example here. So S1 and S2 are in the gold standard. Now suppose that we have 2 systems, System 1 and System 2. System 1 picks the same 2 sentences, 1 and 2. System 2 picks sentences 2 and 4. If we use precision and recall, System 1 is going to get 100% precision and 100% recall because it picks exactly the same sentences. Whereas System 2 is going to get only 50% precision and 50% recall because it picks one of the 2 sentences, and one of the 2 sentences that it picks is correct. So in a sense, we are saying that System 2 is way worse than System 1. Well, this may or may not be the case. Suppose that, just hypothetically, that the ideal summary really should have consisted of sentence 1, and sentences 2 and 4 are about the same level of importance. Because the ideal summarizer was supposed to pick only 2 sentences, she picked 1 and 2. But another evaluator, or perhaps the same evaluator, if asked again, would have picked a different set, maybe S1 and S4, or S2 and S4. So it turns out that there's some arbitrariness in picking 2 sentences out of 10. So if this was the case, then we don't want to penalize System 2 that much. Well, it just was not lucky. It didn't pick exactly the same sentences as the ideal summary, but it came pretty close. So let's look at a more specific example. If we ask the judges to give us not just a plus or minus yes or no decision about each sentence, but rather to give us a utility score for each sentence, how important it is for the summary. Let's see how this changes the picture. So now on the right-hand side, in the left column, we have the ideal summary that consists of the same 2 sentences, S1 and S2, but the judge has explicitly said that the utility of sentence 1 is 10, the utility of sentence 2 is 8. And they have also given utility scores for sentences 3 and 4. Now you can see that S1 and S2 are still the best sentences, But if one had picked sentence 4 instead of sentence 2, or maybe instead of sentence 1, the total utility selected by those two sentences would not be as bad as you may think. So if you pick sentences 1 and 4, you would get a utility of 17 points compared to a utility of 18 points if you had picked sentence 1 and sentence 2. So you're essentially getting a 17 out of 18. That's pretty good. So you shouldn't be penalized if you pick sentence 4 instead of sentence 2. The only penalty that you should get in this case is 1 point that gets you from 8 down to 7. So that's the basic idea of relative utility. So the utility is essentially the percentage of the ideal utility that the system summary picks. Now, this utility can be further expanded into a concept of relative utility, which takes into account also the difficulty of the task. So as in many other NLP problems, we have some sort of a lower bound, which is the random performance. If a system were to pick 2 random sentences out of the 10, what score would it get? And we also have an upper bound that corresponds to what human judges would get on each other's gold standards if they had to pick 2 sentences out of 10. Okay, so now let's see how we can compute relative utility. Suppose that we have 3 judges, judge 1, 2, and 3, and 4 sentences, and we want each judge to pick 2 sentences for the summary. The numbers in the table represent the utilities that each judge gives to the different sentences. So judge 1 gives utilities of 10, 8, 2, and 5 respectively. So if he were to pick 2 sentences, he would pick sentences 1 and 2. Judge 3 has scores of 5, 8, 4, and 9. So if she were to pick 2 sentences, she would pick sentence 2 and sentence 4. So now we can do an experiment. If we pick judge 1 as the gold standard, we can measure the performance of judge 3 against him, or we can pick judge 3 as the reference and judge the performance of judge 1 against her. So let's look at the latter example. So how do we compute the relative utility? Here's how. The best utility that you can get comparing to judge 3 is 17 points, and that is if you pick sentences 2 and 4. Now, if you were judge 1, you would pick sentences 1 and 2. However, those 2 sentences, according to judge 3's utility judgments, get a score of 13. So the relative utility that judge 1 gets against judge 3 is 13 out of 17, or 0.765. And since we have 3 judges, we can have 6 pairs of relative utility scores computed this way. And now, we can compute the performance of each judge against each of the other judges. It turns out that judge 1 and judge 2 would pick the exact same 2 sentences, therefore their scores are 1. But judge 1 would get only 0.765 against judge 3, and so would judge 2 against judge 3. And then if you average all of those values, you would get that judge 1's average performance is 0.883. Same for judge number 2, and judge 3 gets a slightly lower performance of 0.756. And if you average those numbers together, you get the so-called inter-judge agreement for utility selection. So that would give you the upper bound on any system's performance. You don't expect the system to perform better than the judges. Okay, so now we get to the punchline of relative utility. So we're going to compute the following formula. S minus R divided by J minus R. What are those? R is random performance. I'm going to explain this on the next slide, but essentially it's a lower bound on the performance of the automatic system. S is the system performance, so this is the actual utility performance of the system on the current data set. And J is the average of all the judge scores above. D now is a normalized system performance. So let's see what are some of the special cases. If S is equal to J, that means that the system is as good as the interjudge agreement. S minus R divided by J minus R is equal to 1. So that is the highest possible value that you expect to get. If S is equal to R, on the other hand, that means that the numerator of the formula is 0 divided by something that's non-zero. We're going to get a normalized performance of 0. So any system is going to get a performance between 0 and 1 in most cases. If it gets something lower than random, that's possible in theory. We're just going to assume that it was not lucky, it got even worse performance than random. And if it gets something higher than the judges, we can also ignore that because we cannot evaluate something that works better than the judges agree with each other. So how do we compute random performance? It's very straightforward. We just take all the possible systems that pick R of the sentences out of n. So this is the average of all of the systems shown on the top. So for example, for a compression rate of 50%, that means 2 sentences out of 4, we have 6 possible random outputs. They're the ones that correspond to sentences 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, and 3, 4. And for each of those, we can compute the utility score and average all of those to get the value of R. So here's an example. The system that picks sentences 1 and 4 is going to be 0.833. That's the utility against the 3 judges if you pick sentences 1 and 4. The random performance is 0.732, and the interjudge agreement is 0.841. And then according to the relative utility formula, you get an average performance of 0.927. In another example, if your system was to pick sentences 2 and 4, the same formula would give it a relative utility score of 0.963, which is better than the one that picks 1 and 4. And here's a nice way to visualize it. For the system that picks sentences 1 and 4, its performance is 0.833. That's the middle dot in the scale. The interjudge agreement is the upper dot. Random performance is the lower dot. So if we scale up this range from 0.732 to 0.841 to a scale from 0 to 1, the 3 dots are going to appear as follows. R is going to be 0, J is going to be equal to 1, and S is going to be the relative utility, normalized relative utility of 0.927. So this system is actually pretty good. It's much more similar to the judges than to random performance. So let's look at one more issue introduced in the Mead paper, and this is the idea of subsumption across documents. So we have here a news story that has 11 sentences, and another story that has 9 sentences on a very similar topic from the same day from different source. So one thing that we can notice here is that some of the sentences on the left-hand side somehow match with some of the sentences on the right-hand side. So here, sentence 1 on the left gives almost the same information as sentence 1 on the right. Sentences 2, 3, and 4 on the left combined give the same information as sentence number 2 on the right. And sentences 3 and 4 on the right combined give the information that is in sentence 9 on the left. So the idea behind this example is that if 2 sentences contain roughly the same information, according to the diversity re-ranking principle, we don't want to include both of them in the summary. So that's why when people compute the performance of information extraction and summarization systems, they take into account redundancy. So let's see how this is related to subsumption and equivalence. So subsumption is when the information content of a sentence A is contained within sentence B. So A then becomes redundant in the context of B. So the information content of A is subsumed by the information content of B. So we can skip sentence A if sentence B is included in the summary. On the other hand, if sentence B is not included in the summary, then the value of A is still there. And we can also define equivalence. If A is subsumed by B and B is subsumed by A, we can say that sentences A and B are equivalent, and either one of them will be equally good for the summary. So here's an example. Sentence 1, John Doe was found guilty of the murder. In sentence 2, the court found John Doe guilty of the murder of Jane Doe last August and sentenced him to life. As you can see, the second sentence includes 4 or 5 different facts, whereas the first one only includes 1. But that one fact is definitely included in the second sentence as well. So we can say that sentence 2 subsumes sentence 1. So how is sentence subsumption used in evaluating summaries? Let's look at the previous example with the speaking 2 sentences, but now instead of judges in the columns, we're going to have 3 different documents. So we just have essentially a set of 12 different sentences, and we want to determine which ones to pick as the summary. If we wanted to pick 2 sentences right now out of those 12, which ones would we pick? Well, it's pretty obvious that we would want to pick sentence 1 from Article 1 and sentence 1 from Article 2 for a total utility of 20 points out of 20. Now, but imagine that sentence 1 in Article 1 subsumes sentence 1 in Article 2. And similarly, sentence 4 in Article 2 subsumes both sentences 3 and 4 in Article 3. Well, in this case, which two sentences are we going to pick if we wanted to produce a two-sentence summary? Well, we're probably still going to pick sentence 1, article 1 with a score of 10. But now we don't want to pick sentence 1, article 2 as the second sentence because it's irrelevant and it's useless. Instead, what we're going to do is pick either sentence 2, article 2, or maybe sentence 4, article 3, which would give us 9 points instead of 10. But at least that's the best that we can get in the presence of this redundancy. So modifying the formula for mean, we have again the sum of all the different features for the sentence, the centroid, position, and frequency, but now we also want to discount the redundant sentences, the ones that are subsumed by the others. And so the formula used in mean is based on the Jacquard coefficient between the two sentences. So another metric for evaluating summaries is the so-called pyramid method. The pyramid method was introduced by Annie Nenkova and Rebecca Passano in 2004. And it's used for multi-document summarization. It's based on the idea of semantic content units. So what are semantic content units? Well, they have to deal with different statements or facts that are realized using different formulations. So there may be two different ways to say the exact same thing. So here's an example. We have 4 inputs, A1, B1, C1, D2. There are 4 different sentences. And the text that is underlined is repeated. So we have one content unit, SUU1, which appears in 4 of the sentences. The fact that 2 Libyans were officially accused of the Lockerbie bombing, this appears in all of the 4 sentences. We have a second SCU number 2, which appears in 3 of the 4 sentences. The fact that the indictment of the 2 Lockerbie suspects happened in 1981. So the weight of SCU1 is 4, and the weight of SCU2 is equal to 3. So what that means is that if we want to produce a summary, and that summary happens to mention the fact that 2 Libyans were officially accused of the Lockerbie bombing, it would get 4 points. If instead it just tells you that they were indicted in 1991, you would get 3 points. So everything that you include, any SU that is included in the summary gets points in proportion to the number of reference documents in which it appears. So here's an example from the Nenkova and Passano paper. You have this kind of pyramid where the SCUs that appear in the most documents are shown on the top of the pyramid. Then you have the ones that appear below and so on. The ones at the bottom of the pyramid are the ones that only appear in one of the reference documents. So what are the optimal summaries that include 4 SCUs? Well, clearly every optimal summary would include the 2 SCUs with a weight of 4. And since you have room for 2 more SCUs, you would have to pick 2 of the ones that have a weight of 3. And any 2 out of the 4 SCUs with a weight of 3 would be equally good. So you shouldn't be penalized if you pick a different set than the one that was used in the reference summaries. So a pyramid, in a sense, is a variant of relative utility, where which is much more knowledge-based, because the SCUs are based on actual understanding of the document, whereas relative utility is based on the importance of entire sentences. Okay, so before we conclude this section, I want to mention some of the important corpora available for text summarization, which are used in many different papers for evaluation purposes. The first ones to mention are the ones used in DUC and TAC. So DUC and TAC are NIST-based evaluations similar to TREC. And if you remember, TREC was a text retrieval conference, whereas DUC is the Document Understanding Conference, and it has been superseded by TAC, the Text Analysis Conference, both of which have been very popular in the last 10 years. So the corpora that we use there include both single and multi-document summarization corpora, and they're available in the DUC and TAC respective websites. Another corpus is SumBank, which includes English and Chinese language documents and summaries, both manual and automatic, and evaluations based on relative utility, and precision and recall, and many other metrics. This one is available from summarization.com. There's also the SUMMAC corpus and the New York Times corpus, which is a collection of news documents and non-extractive summaries of those documents. That corpus is available from the Linguistic Data Consortium at the University of Pennsylvania. There are many other corpora available for text summarization evaluation, but I would like to focus just on these because I think they are the most influential ones. So this concludes the section on evaluation of summarization. The next segment is going to be on sentence compression.